A recap of exponential equations, something like this. 5 to the power of x equals 125. Well, that's not a big deal because we know 5 to the power of 3 is 125. We could answer that quite easily. Ooh, a little bit trickier. 4 to the power of 2x plus 1 is 1 on 2 root 2. But of course I can rewrite 4 as 2 to the power of something. And of course on the right hand side that's 2 to the power of minus 3 on 2. So equating the powers, great, we can get x equals minus 7 on 8. But then we get ones like this. 7 to the power of what is 32? I can't really rewrite 7 as 32 to the power of something, and I can't rewrite 32 as 7 to the power of something. And that's of course where our logs now become useful, because we can say, hang on, this is the same as x equals the log of 32 base 7. Unfortunately, our calculator doesn't have a log base 7 button. But we do have this wonderful little formula, the change of base. So we can change it to a base which we then can put into the calculator. Now, our calculator, of course, has two different log bases there. We've got log base 10, which is the LOG button, and we have the natural base. So log base E, the LN button. If we do want to change the base, it's quite a simple thing to do. It's just we change the base to whatever we like, and it's still the log, in this case of 32, but we then divide it by the log of the original base, so log 7. Again, it does not matter which one of those buttons I press, as long as I press the same one for both of them. And we get 1.781. And if we are unsure, and you don't believe me, you can go to a calculator right now and go, what is 7 to the power of 1.781? Well, it won't be 32 exactly, because that's an approximation, of course, but it should be pretty close to 32. So 3 to the power of x equals 5 to the power of x minus 2. Just log both sides. And again, it does not matter which base we use, as long as we use the same one in any calculations. I can bring the powers to the front. I want to make x the subject, and here we go. 2 log 5 over log 5 minus log 3. And we get 6.301. Exponential equation here, it's actually a quadratic, because of course 9 is 3 squared. You could substitute in a pronumeral for 3 to the power of x. M is equal to 3 to the power of x, so therefore you could work out that m squared, and eventually with a bit of manipulation, oh yeah, that actually is 9 to the power of x. So really I've got the quadratic equation, m squared minus 4m plus 3 equals 0. Factorise that, either m is 3 or m is 1. Substitute back in what I let m be. 3 to the power of x is 3, or 3 to the power of x is 1, and they're two very simple exponential equations to solve. We get x equals 1 or x equals 0. As I say, you may not use that substitution, because you could just look at that and realise the pronumeral is 3 to the power of x and go straight to something like this. Whilst talking about logs and exponentials for that matter, just going to make a note about this. In equations, when we're solving an equation with continually increasing or continually decreasing functions, when you're playing with equations and inequations, what you're basically doing is, yes, we're doing the same thing to both sides, but what we're doing is we're applying a function to both sides. If we apply a function that is continually increasing to both sides of an equation, the inequation sign stays the same. But if I apply a function that is continually decreasing, the sign changes. That's why if I was solving 1 over x is greater than 3, okay, it's a very simple one. Normally we'd look at that and say, oh, well, if I turn both sides upside down, I change the inequality sign. Let's forget about the x can't equal 0 part for now. But what you're really doing is applying a function. You're applying the function, let's call it, say, function z is equal to 1 on z. You're basically applying that function. And so when I put 1 on x into this function, I get x. And when I put 3 into that function, I get a third. But if you look at the actual function y equals 1 on x, that is continually decreasing. So therefore, the inequality sign changes. So that's the real reason why, when we take the reciprocal, it changes. We're actually applying that function. So alright, let's apply it to something like this. If I've got 1 is less than 2 to the power of x is less than 32, our exponential function and our log function Well, both of those functions are continually increasing functions. So if I apply that function to each piece of this inequation, the signs are going to stay the same. So the log of 1 is less than the log of 2 to the power of x is less than the log of 32. And I'm going to use base 2, makes sense because my exponential is base 2 as well. And so I'm saying the log of 1 base 2, well that's 0. Log of 2 to the power of x base 2 is x, because the x comes out the front. And then the log of 32 base 2 would be 5. So x is in between 0 and 5. If I wanted to solve this one, now I'm going to apply the exponential function to both sides, because to undo the log I would, and I don't know if this is a real word or not, I'm going to exponentialize both sides. If it's not a word, it should be. So we get 3 to the power, makes sense to use base 3. 3 to the power of log x base 3 is greater than 3 squared. X is greater than 9. Let's play with 8e.